Modern heavy-duty engines operate under a conflicting set of mandates. To meet Euro 6 standards and beyond, a single engine must simultaneously produce maximum pulling power, absolute fuel efficiency, and exhaust that is nearly free of particulates. These three goals are physically at odds. Generating more power typically requires more fuel, which increases raw emissions. Traditional mechanical systems, governed by fixed gears and springs, lack the precision required to balance these variables in real time. The difference lies in the control method. While old mechanical pumps rely on fixed physical reactions to the throttle, modern engines use a proactive digital architecture to govern the combustion process. This is the core of digital diesel intelligence. The gas pedal no longer dictates a physical flow of fuel, but instead sends a request to a central processor that evaluates every input against a complex set of operational constraints. This digital brain is the smart ECU. By processing millions of data points every second, it resolves the conflicting physics of modern hauling, managing power and efficiency in the same micro moment. To maintain this level of control, the engine relies on a sensory network woven directly into the metallic architecture of the block. This schematic identifies the critical inputs feeding that network. Sensors track internal dynamics at extreme speeds, monitoring common rail fuel pressure as it reaches peaks of 2,500 bar. Specialized piezoelectric microphones act as the engine's ears. They listen to the high-frequency vibrations of the combustion chamber, identifying microscopic explosive anomalies the moment they occur. The smart ECU fuses these individual streams of pressure, temperature, and acoustic data into a single cohesive stream of telemetry. This fusion creates a virtual twin, a real-time thermodynamic replica of the combustion chamber. By modeling the current state of the cylinder, the system calculates the exact physics of an explosion before it ever happens. This computational foresight allows the engine to correct combustion physics in the milliseconds before fuel is injected into the chamber. Now, those digital calculations must instantly translate into a violent, highly controlled physical action deep inside the dark combustion cylinder. The instrument of this precision is the intelligent piezoelectric injector. These components are fast enough to open and close their microscopic internal valves up to 7 times in a single millisecond. This timeline breaks that millisecond into targeted phases. It begins with the pilot injection, a superfine mist that pre-warms the chamber to eliminate traditional diesel clatter. Once optimized, the main injection fires. This high-precision volume of fuel generates the primary burst of heavy-duty torque. Finally, the post-injection phase burns off residual soot and heats the exhaust filters, ensuring the system remains clean. Dissecting a single explosion into these 3 phases is the physical mechanism that allows the engine to stay powerful, efficient, and clean simultaneously. The engine's intelligence eventually moves beyond the internal cylinder and begins to factor in the external geographic environment. Using GPS topography, the system evaluates the terrain miles ahead. In this example, it identifies a steep mountain incline 2 kilometers before the truck arrives. To prepare, the ECU pre-spools the turbo and recalibrates fuel pressure proactively. This eliminates power lag entirely before the truck even hits the slope. This foresight is also applied to the engine's internal health. By monitoring its own operational data over time, the system can predict mechanical decay. The diagnostic precision is microscopic. The AI can detect an electrical current variance caused by a 12-micron flaw forming inside a high-pressure pump long before the part fails. By integrating external terrain data with internal hardware tracking, the engine preemptively adjusts its state to meet a future condition before it actually arrives. These microscopic detections trigger logistical actions. The system alerts fleet managers to replace stressed components, such as a failing injector, up to 1,500 kilometers before a breakdown occurs. The engine also features self-learning capabilities. As parts wear down, the ECU mathematically recalibrates injection duration to compensate for the physical changes in the metal. This telemetry transforms the truck into an active telematics node, continuously beaming millions of daily combustion data points to centralized cloud servers for fleet-wide optimization. This constant mathematical recalibration preserves day-one factory efficiency and emission standards for engines with over 500,000 kilometers on the odometer. By anticipating terrain, compensating for wear, and preempting failure, Digital Diesel Intelligence has engineered a path to the ultimate logistical goal: